ham radio is supposed to be fun too. So if you have people who aren't into CW or digital modes, but they really like phone contests, well, why can't they participate too? So we did that. And we had a really good response for this. We successfully processed 570 logs, and there were almost 30,000 QSOs in the submitted logs. That's great for this contest we just came up with. And then RBN, PSK Reporter, WhisperNet, they performed great as well. So RBN, we got over 600,000 spots for that, the SDQP period. WhisperNet, same thing, over 630,000 spots. PSK Reporter, over 1.2 million spots. Yeah, it was great. So once we ran this whole thing, it was my job to figure out what to actually do with the data. And I decided I wanted to focus on the CW data. I was like, I feel like CW is very ham radio, and so I just focused on the RBN observations. And this is what I found. I was able to make this plot like this plot you see here. Now the little black dots are CW stations that were participating in the SDQP. Were there any CW operators here who participated in the SDQP? No? So usually like at Contest University, there's a lot of good CW contest operators. We had a few people raise their hand, so I had them come up to the board, and they had this circle point out where their dot was. I had them point that out. So the little black dots are the actual CW transmitters. The blue stars are the RBN, Reverse Beacon Network, automated Morse code skimmer node locations. And then the colored dots, every colored dot represents a spot observed by the RBN, and I've plotted it at the midpoint between the transmitter and the receiver. And the reason I put it at the midpoint is because I'm assuming single hop propagation. I'm assuming that's the point where the ionosphere is being measured. It's color-coded by the maximum amount of eclipse obscuration for that particular location. So you can see this dark red here is 100% eclipse, and so you can see totality go across the United States in the data. Yes?
You actually find hams are willing to stay indoors during the eclipse?
We gave 100, no, we offered it to be like field day style. So we gave bonus points if you operated outside so you could see the eclipse as you're operating.
I wouldn't be indoors, come on.
Yeah, well, we didn't expect it. I went down, this was a week before I got married. Actually, it was less than a week before I got married. I got married August 26th, and this is August 21st. So, my fiance and I, at the time, we drove down with a bunch of friends to Kentucky. We stayed at the Moores Resort out there. We set up dipoles in the trees and little tents outside, kind of field day style, and we tried getting the station going and made sure we could see the eclipse all at the same time. So somehow it worked. And we got enough data. So here's the actual observations where you can see the actual eclipse effects.
Yeah.
So,
you anyway.
yeah, I know, right? That's love.
Anyway.
She did marry me. That is love.
And she has her license.
Yeah,
She has a license. Yeah.
she's also a magnetospheric physicist.
Lucky guy.
And a material scientist. She before we got married, she was working in the clean room at SRI, and as a process engineer making chips. So, when we were having the chip shortage issues, I kept asking her, I'm like, can you just build a fab in our barn so we can solve our problem?
Not clean enough.
Yeah, that was the problem. It wasn't clean enough. Anyway, so here are the actual observations from the eclipse on top. That's the observations, and then this is the model on the bottom. So yeah, so the top, this is actual RBN Reverse Beacon Network data. Actual ham radio data for 14 megahertz. And on the x-axis is time, with 0 being the point of maximum eclipse. All the way to the left is 1.5 hours before maximum eclipse. All the way to the right is 1.5 hours after maximum eclipse. The y-axis shows the distance between transmitter and receiver from 0 to 3,000 kilometers. And then this little dashed line in the middle tells you when you had the phase of the eclipse. So when the dashed line is lowest, the eclipse was maximum and it was most darkness. So an hour and a half before the eclipse, 20 meters was, nice and wide open. People were communicating between 1,000 to 2,000 kilometers in range for a good, up to about an hour, 45 minutes before the eclipse. Then the eclipse took hold and the ionosphere weakened and the band started to shut down, just like you'd expect it to shut down as you go into night. And it got worse and worse and worse, and then gradually it got better as the eclipse ended. Never fully recovered, but you do see the recovery there. So you get this really great eclipse observation there. And then we used that ray trace modeling with SAMI3 like I showed you before, and I created a theoretical grid over the United States of where I'd have a bunch of theoretical transmitters, and then I used the actual RBN locations, and we wrote a script and ran it on the supercomputer cluster at NJIT to do a ray trace between every transmitter and every receiver at a 3-minute cadence for all of the SEQP bands for the duration of the SEQP, and then we were able to plot those results in the same form as I have plotted this, so you could compare it one against the other. And really, Joe Cuba, who did the SAMI3 model, he described this at the AMSAT workshop this year as a spectacular result. Okay? And what he meant by spectacular was that, not that it was perfect, he said it showed, it was really good. It was good promise. So you can definitely see that the model captures the main features here and here, but it's not quite perfect. So it's more narrow here, it's wider up here. Maybe you see it's a steeper recovery here, more gradual recovery here. So there's enough differences that you can go back to the NSF and say, we need to do this again. So that's the definition of a spectacular result.
Yeah, more study, more grants.
Right. So here is, so we did it for, we had good data for these 4 bands, and so on the left-hand side, you can see the observations. On the right-hand side, you can see the model. The X and Y axes is exactly the same as you saw before. So an hour and a half before the eclipse, an hour and a half after the eclipse, and then 0 to 3,000 kilometers. I know you can't read the actual numbers here, but same format as before. So now you can see 14 megahertz shut down during the eclipse, 7 megahertz went long. 3.5 megahertz and 1.8 megahertz, they were closed before and after the eclipse because of why?
Noise.
The D layer, right? The darn D layer. There's D region absorption. The eclipse came, the D region recombined, the band opened up, and so you saw that beautifully. Now, when we looked at the model, I found that I had to split the model up into refractions off of the E region and refractions off of the F region to get agreement. So here, these are the model successful contacts for refractions happening below 125 kilometers altitude. So basically, modeling contacts coming off of the E layer. This is where you had the spectacular result on 14 megahertz with the E region. We did not have a spectacular result or a good result at all with 7, 3.5, and 1.8 megahertz. Now, if you look at the F region, we had very good results with 7 and 3.5 megahertz, so you could probably say spectacular again, not with 14 megahertz. So here we're showing that the F region matches 7 and 3.5, but not 14. 1.8 megahertz is a little bit different. I can explain this, how do I explain this succinctly? I think the model was actually, the electron densities were set a little too high, and it didn't. There are reasons that this one didn't work, but the other 3 did work. So it was a very interesting the result here. Before going into this, I would have just naively thought, I'm like, okay, 14 megahertz is probably F region propagation for most of the time. That wasn't what the model showed. The model showed it was actually E region propagation, and the model also gives us takeoff angle information. So all of the rays that were successful had takeoff angles of less than 10 degrees, so low horizon sort of stuff. Whereas the low bands they were all successful if they were coming off of the F region using high angle elevation angles. So really, really interesting result. I think the other neat thing is that we actually, if you just take the RBN data on its own, you can't tell whether it's going off of E or F region, and you can't tell is it low angle or high angle, but by looking at the data in aggregate this way, and by using the model, I think we now have a pretty convincing case of saying more or less what was happening. I think that was really cool. So we have the opportunity to do this again, and we have the opportunity to do it again twice over the next year, and then we won't have the opportunity again for another like 50 years. So I think we all better do it now. Okay? So there are two, the one in October is an annular solar eclipse, that's October 14th, 2023, and then April 8th, 2024 is a total solar eclipse. So a total solar eclipse, of course, is where you have the moon's disk completely cover the solar disk, and you have you just can see the corona around it, and this is kind of the holy grail of eclipses, the thing that everyone wants to see. Then an annular eclipse is when the moon is a little closer to Earth. I'm sorry, when the moon's a little farther away. So as the moon gets farther away from Earth, it looks smaller. Then it doesn't cover the whole sun. It just fits inside of the sun, so you have this ring of annularity. So it's an annular eclipse. And then in here, you're only going to see annularity if you're in this region here, and you're only going to see total solar eclipse if you're in this region there. Everywhere else in the United States will at least see partial eclipse. So you'll get at least part of the moon covering the sun. So I made these little animations showing the path of the eclipse. This is the annular eclipse coming up. And what's really cool here is you can see we're not only getting annular eclipse over the United States, but it's also going down into Mexico, into South America. So I'm thinking when we do the solar eclipse QSO party again, we need to make it a, not just the United States, but all of North America, all of South America. So we need to try to get the other hams in other countries participating in it as well. And here it is for the total solar eclipse in April. And if you want to make these maps yourself, the code is, I made it open source on GitHub, so you can go download that code and run it yourself. I also ran these cases for like every altitude from 0 to 450 kilometers altitude at 50 kilometer steps. And I have it all run, and I have that on this Noto thing. So there's like 50 gigabytes of eclipse predictions that you can just go download. But so this is just telling you the percent obscuration. This isn't actually telling you what's going on in the ionosphere. So I gave these outputs to Joe Huba, who has SAMI3, and he ran SAMI3 using the eclipse tracks that I gave him with my code. And so this is what was playing all through dinner. This is differential total electron content using SAMI3 during the annular eclipse in October. So what he did was he calculated what the day would be like without the eclipse, and then he calculated the total electron content for there, which means you start at the ground and you add up all of the electrons from the ground all the way up into space. And so he did that for the day without the eclipse. He did it for the day for that same day with the eclipse predicted in, and he subtracted one minus the other, and then he got this result. Okay. Do you see, so when you see this, is there anything surprising you in this prediction? Yes. That surprised Joe, too. When we first got on the telecon with him, he was like, I've got these results. And he's like, and there's something that surprised me. And we're like, what surprised you? He's like, yes, that. So that's a plasma bubble. And that plasma bubble only shows up in the eclipsed version of that particular day. So there's some sort of plasma dynamics going on that when you have the eclipse going into the equatorial region at dusk, that forms conditions that will create this plasma bubble that if you didn't have the eclipse, he's not predicting. So now he's calling up his friends at the NASA Gold satellite mission, which he says he believes that they could actually see this prediction. You know, maybe we could see it in our SCQP as well. It's going to be a little tricky, but it's possible. But I think
South Atlantic anomaly has everything to do with that?
it might have something to do with that too. That's a little like dip over here, but yeah.
To get their Brazilian friends to.
So that's an interesting thing to look at. You can also see the equatorial atmospheric anomaly there as well. So we have, with these two eclipses, we didn't want to just do, so one of the things about running HAMSAT is it's not just what I want to do. We have all these volunteers and all these different people, and they all have like different ideas on what they want to do, and a lot of it's driven by what people find interesting. So we decided that with two major eclipses like this, it wasn't enough just to do a single solar eclipse QSO party. We needed to do a number of different things that met a number of different people's interests. And so we came up with this idea of having a number of festivals. So we're having the HAMSAT festivals of eclipse atmospheric science, which has many different experiments. And so here are the experiments that we have pretty well organized, set, and ready to go. So we have the Solar Eclipse QSO Party, which is our traditional ham radio contest. We have the Gladstone Signal Spotting Challenge, which is a contest for skimmers and spotters. So if you like operating RBN skimmers, or you like operating WhisperNet skimmers, you can now actually enter your skimmer in a contest to see if your skimmer spots more spots than someone else's skimmer. We have the GRAPE HF Doppler experiment, which uses a GRAPE personal space weather station, and then we have the time difference of arrival TDOA experiment. And there's more. So those are the ones that we have rules up for. We have good plans. Our friend Jonathan over here, he's doing VLF science, and he would love nothing more than to cover the entire globe with VLF receivers and do some sort of coordinated eclipse experiment. Maybe TAPR can help Jonathan get things out so he can help him realize his dream.
Maybe we can.
You can. So all of the information about this is at hamsci.org/eclipse. I'll go over some of these things. So for instance, you have to have science questions. For the solar eclipse QSO parties, we're asking things like, can the annular eclipse be observed in HF communications? We know the total solar eclipse can. Can we see the annular eclipse? How large is the disturbance? How long before and after maximum eclipse are the eclipse effects observed? Is an onset recovery asymmetry observed? Will the results again suggest the E layer propagation for 14 megahertz and F layer for 1.8 to 7 megahertz? Or, now that we're going to a higher part of solar cycle 25, are we going to see something different? How similar are the effects of the eclipse to dawn and dusk? So each of these things are going to be 10 hours long on the days that I've talked about. The Solar Eclipse QSO Party, we reviewed the rules of the 2017 Solar Eclipse QSO Party. We tried updating them in ways that we thought were appropriate. All of those rules are available on the website. For the rules, we're encouraging, again, all modes, digital, all varieties, CW, phone, bands. Of course, you can just only use the contest bands, so no WARC bands. We're giving recommendations for where to call CQ, SCQP, on the 38s for CW and sideband. And for digital modes, you want to use the usual activity centers, but you can please spread out. The exchange. Okay, which part of this slide do you think got a really hard laugh from the people at Contest University?
You got the 589.
Yes.
Yeah.
Yeah, but basically that, or the very first bullet. I want all of you guys to give us accurate signal reports. You would not believe the laughter I heard when I told this at Contest University.
Yeah.
But I told them, I think when I do this, all of the science I've published with the RBN and WhisperNet and PSK reporter data, so far I have not made use of the signal reports at all, even the automated ones. I found them very difficult to work with. So far, all of the science I've actually published, I've been able to do by just using the fact, is the signal reported or not, and then I'm able to see these patterns that correspond with other things. But I told them, for this particular contest, it'd be nice to do the actual signal reports because maybe you will be able to see in your own signal reporting some sort of patterns that you didn't recognize otherwise. So, we're doing that.
Is that Ward Silver's call sign?
Yes,
Yeah, I
yes,
thought
that
so.
is Ward Silver's call sign, you're right. Good eye. All right, so, yeah, and Ward was one of the people instrumental in helping with the rules for the first SEQ base.
And it's on the ham side board.
And it's on, yes, and he's on the AMSAT board. So there's all these things. So yeah, so the scoring, typical contest fashion, QSO points times multipliers plus bonus points. You get 2 points. I already went over that. The multipliers are 4-character grid squares, so try to work as many grid squares as you can. That'll help spread things out. The last line here is also fun for contesters. Dupes are allowed every 10 minutes.
Ooh, yes.
Yeah, oh. So, what? Yeah, right, exactly. So, I mean, hopefully we can, if we're looking for, 20-minute waves, we'll be okay. So,
Just barely.
just barely, just barely. But yeah, so we're doing dupes allowed every 10 minutes. It's to monitor changes in propagation over a particular path during the eclipse. And then, yeah, so the bonus points, I don't have the bonus points listed in this presentation, but if you go online, you'll find you get bonus points if you operate during totality or max annularity. You'll find out you get 100 points if you operate outside, so you can see the eclipse while you're operating. You get 100 points if you operate in a public venue, that sort of thing. You get extra bonus points if you send in engineering information about your station, so you could go back and look for those things. Okay, so that's the SEQP, but then yes, you also have this Gladstone Signal Spotting Challenge. That's our other contest. This is a contest, as I said, for people who like running skimmers or operating Whisper or FST4W, which is a beacon-like version of FST4. And this is named after Philip Gladstone, N1DQ, who is the founder and operator of PSK Reporter, which is making a lot of our data possible. And the scoring here is 1 point for every spot received. You get multipliers for operating FST4W-120 because that Rob Robinette is doing, Quinn Griffiths, they're doing things with that to do better detection of spectral spreading. So they think they can get more interesting data if you're using that than just plain old Whisper. Again, you get multipliers for uploading engineering information on your station. So that is so those two contests I kind of put in more like the big data kind of random, a little more chaotic sort of experiment, a little less planned. We do have some, which I think we're going to get really, really interesting and valuable results from, but we also have a few experiments where things are a little more done in more of a traditional scientific manner, where we're trying to make precision measurements, or we're trying to make precision measurements or do things a little bit more systematically. So one of them comes out of the Personal Space Weather Station eclipse experiment. So this group is well versed in the Personal Space Weather Station project because we've been working so closely with TAPR. But I do see some people in the room here who may be new. So the Personal Space Weather Station project is a project to develop a ground-based modular system that can remotely sense space weather. And here's the basic block diagram for it. So at the core, you have some sort of a radio, like a software-defined radio. We're trying the Tangerine SDR. That's attached to HF antennas. This radio requires a highly stable oscillator. So we're using like a GPS disciplined oscillator, which is providing us with precision frequency measurements and precision time stamping. We have a computer. It's attached to a computer, so we can do local number crunching and analysis. And then it's modular, so another one of the things we have on the Personal Space Weather Station is the ground magnetometer. Anyone know why we care about ground magnetometers if we're radio operators? I know. Okay.
Earth magnetic field?
The Earth's magnetic field, yes. How many people here have heard of the KP index? Okay, so the KP index is a major index that we use. It's one metric we use to predict how the HF radio propagation is going to be at a particular time. And that KP index is all derived from ground magnetometer data. So you can use the ground magnetometer data to remotely sense these currents going on in space, and that is tied into radio propagation as well. Then we also have VLF receivers, which again, the VLF receiver is here because of my friend Jonathan, who has a lifelong passion for VLF. And when I first met Jonathan, I was just starting as a professor at the University of Scranton. He was a student there, and he was a ham. He was the only ham I knew in the department. So I thought he'd be great working on this. And of course, my interest is in HF. And I talked to him a bit, and I found out he really wasn't interested in HF. But he's like super interested in VLF. And you know, one of my things is, as a leader of AMSAT, I think it's really important to match people's work up to what their passions are. So I'm like, he's so interested in this, I can't not let him do it. So that's why the VLF receiver's there. And it turns out you get great observations from it. So yes, this is a multi-institutional team. We've got Scranton is leading the project. We're working very closely with TAPR and the University of Alabama and Case Western, NJIT. We have the MIT Haystack and Dartmouth involved. Most of our funding is coming from the NSF, and ARDC has graciously funded some of the Tangerine SDR effort and also provided additional funding for the AMSAT workshop this year. So we have the ground magnetometer is developed primarily by TAPR with additional inputs from NJIT. And if you want one of these things, you can go talk to this gentleman over here, George. He will be happy to.
I will kit you out properly.
Yes, he will kit you up properly, so you can buy one of these today. And then over here, again from my friend Jonathan, we have the Whistler Catcher VLF leaf module, but he has a standalone receiver that he's prototyped and we've installed in my backyard. So you can see him standing right by his active antenna there. I really had to put a lot of sweat equity into this, digging this trench and laying this pipe. There's my house over there, so the VLF's over there. But you know, it's really paid off. So here's some nice observations he's gotten from the installation at my house. This is a Whistler event, and what a Whistler is you have lightning that happens, say, like in the southern hemisphere, and that lightning releases broadband electromagnetic energy that goes up, mode converts, and propagates along magnetic field lines out into the magnetosphere. It experiences frequency dispersion, and then when it gets to the other hemisphere, like the northern hemisphere, you hear this Whistler sound, which I will now play for you. You hear that? Yeah. Jonathan has the biggest grin on his face. He has it set up so you can actually listen to this live over my Starlink connection. Yeah, so you can talk to him later for the
For the URL.
For the URL, yes. Yeah. And then this is another really nice observation he got. It's something called a dawn chorus event. So any birders in here? Yeah? So what's a dawn chorus event?
It's what you hear at dawn when all the birds start waking up.
That's right.
Yeah.
So you hear that dawn when all the birds start waking up. And so you actually can have similar VLF sounds where that if you play it, I don't have the audio recording in here. It's my fault, but if you play it, it sounds like the dawn chorus of birds. So that's where the dawn chorus comes from, the name. But it also turns out that this particular phenomenon also happens just at like local dawn. That's where you hear it in the radio too. And this is because you have energetic particles typically associated with auroral type events, something we call substorms, coming in from the magnetotail, coming towards Earth, getting pushed, the electrons are getting, energetic electrons are getting pushed around to the dawn side of the Earth, and then you're getting these plasma interactions that are creating these VLF waves that you see right here that eventually get heard on Earth. And so this is neat because there's actually a network of these VLF receivers. So there's one run by Mike Smith in Forest, Virginia, and you can see the Whistler, I'm sorry, not the Whistler, the Dawn Forest event signatures there. And then here at my house, the observatory that we run, you can see the Dawn Forest there as well. And it's actually stronger over at my house than in Virginia. It's very nice. So that's the VLF system. And then of course we have the other systems that we're developing here, the Tangerine on the right, which we're still working on. And then on the left, we have the low-cost Grape personal space weather station designed by Case Western. So the Grape is it's a very specialized radio receiver. It's not really a general purpose radio receiver that you use for listening to communications or music or anything like that, or transmitting data. Its primary objective is to measure the Doppler shift of HF standard stations such as WWV and CHU. Now WWV, it's in Fort Collins, Colorado, WWVH in Hawaii, CHU, these stations are all designed to have very stable frequency references. They have atomic clocks there, providing the stability. So you expect that when you measure the frequency of the carriers that these stations produce, you expect it to just be straight across. So if you're listening to 10 megahertz WWV, you expect it to just be 10 megahertz out to like, 10 to the minus 13th or something like that. But in reality, that's not what happens unless you live like right next to the station. And that's if you have a receiver that also has very good frequency stability, which you can get using a GPS discipline oscillator, well then you can see these variations, and those variations can be attributed back to variations in the ionosphere. And so that you can see over here, you have WWV over here, you have a receiver over here, the signal goes up, and then the ionosphere can either move up or move down, or the electron densities can change, and ultimately the path length changes with time, or the velocity of the signal changes with time, and that puts these Doppler shifts onto your received signal. And so that's what this little device is designed to measure. So we have two versions of this. We have the Grape version 1.12, which is a single frequency unit, which kind of looks like this. You can build it yourself, and it's available now. So if you want to set up your own Grape version 1 station, you can go to AMSAT.org/Grape, and you can buy the board off of OSH Park. We have the BOM posted. You can order the parts. We've had it checked out recently, so you should be able to get everything. And you need to get a Leo Bodner GPS discipline oscillator, and then and a Raspberry Pi, and then you should be good to go. The Grape version 2 is a 3-frequency, can do 3 frequencies simultaneously. It will be pre-assembled. We're currently building the prototypes now. John Gibbons, NAOBJ, the engineer at Case Western, he is taking the charge on this. So we're going to use this to study the upcoming eclipses. So I'll show you some data taken not by a Grape, but by someone who's using a similar technique during the last eclipse. WA9VNJ, who's unfortunately now a silent key, he gave us his beautiful observations taken on 10 megahertz, listening to WWV from Milwaukee during the last eclipse. And so this slide here, the top figure is the control day, August 20th, 2017, the day before the eclipse. The bottom figure is August 21st, 2017, the day of the eclipse. And so let's look at the control day first. You see the dashed red line here? That is the solar elevation angle. So right here in the middle where it's highest, that is noon. And then here at the beginning, that's dawn. There at the end, that's dusk. Now, as dawn comes up, you expect the ionosphere to become more ionized. That leads to more refraction. The path lengths are growing shorter. As the path lengths are growing shorter, you get, with time, you get positive Doppler shift. It's exactly what you see here. At the end of the day, when you go into dusk, the ionosphere is becoming less ionized, the refraction is becoming less, the path lengths are getting longer, you get negative Doppler shifts. so we see that there. Interesting, what is this spike here? Anyone know?
Solar flare?
You are absolutely correct. Have you heard this presentation before?
No, I've listened to the presentations long enough to begin to understand the science.
Amazing. It is a solar flare. So yeah, so solar flare happened. You can go look at that in the GOES X-ray data, and you can see that leads to sudden burst of X-ray energy, which will ionize the D region, suddenly cause a shortened path, and you get this flash of Doppler. So that is a solar flare. Okay, let's look at the eclipse day down here. You get a gold star, George, by the way.
Oh, but so I must confess, I remember the history of the day and the fact that there was a solar eclipse, a solar flare as well. So
Well, you still get a gold star.
thank you.
You're welcome. so over here, you have the day of the eclipse. So now you've got the red dashed line again showing solar elevation angle, but now you also have this line here showing the percent obscuration. So you can see down here, this is where there's maximum eclipse. So again, you have the positive Doppler shifts at dawn, the negative Doppler shifts at dusk, just like control day. But now, when the eclipse comes on, you have negative Doppler shifts just like at dusk, and you have positive Doppler shifts just like at dawn. So really nice observations. But now look at all of this variation in noise right here. What do we make of that? Well, it turns out the way we've been making the recordings with the grapes and the way he made the recordings here, we're making basically one frequency measurement every second. And it turns out that you really don't want to just do that. You really want to measure a spectrum of frequencies. And so, okay, so you can actually get all this sort of variation. So this is also from a grape version 1, but now we're recording the full spectrum. And you can see how complicated it is. This is through the night. You can see these traveling atmospheric disturbances here. And then here's where you really get a lot of noise in the frequency tracking algorithm. You can get this mode splitting where you get multipath. So here it's coming off of the F layer, here it's coming off of the E layer. This was recorded by Bill Engelke, AB4EJ, down in Alabama. Here are more examples of this from Steve Serwin, WA5FRF, listening to 5 megahertz WWV from Micah, Texas. On the top are 5 examples of recordings at dawn, and on the bottom are 5 examples of recordings at dusk. And look how different every single one of them are. Yeah. It's beautiful. And you get this multipath mode splitting, where sometimes you get these really discrete different traces, sometimes you get this kind of spread or diffuse behavior. You can get these little traveling atmospheric disturbances on here. And the frequency deviations here, these boxes I think are each 1 hertz. So, you know, when you go back over here, you can see these variations. It's like 0.1, 0.01 hertz. So this is why you really need that good GPS disciplinostic to make sense of this. But it's just really, really, really nice. So these are observations Steve Serwin has given us. And then this, I love this plot. John Gibbons, NAOBJ, gave this to us. 10 megahertz WWV over almost 2 years. Okay? Yeah, so the blues are positive Doppler shifts. So the darkest blue is plus a half a hertz, the darkest red is minus a half a hertz. And then the x-axis is 2 years, and then the y-axis here is midpoint local time, so halfway between WWV and Cleveland, Ohio. So noon is right in the middle, and then midnight is at the end. And look at this. You can see the positive Doppler shifts at dawn, just like we saw in the earlier plots. You can see the negative Doppler shifts at dusk, just like we saw in the earlier plots. But now you can also see the seasonal variations. Look, the summer times have more daylight, so you can see that curve there. The winter times have less. So it's just a great way of seeing. And this is with the simpler, the non-spectrum approach. You can see what nice measurements you're getting from this when you put it all together. It's really cool. So this project was funded by the NSF for the next 3 years. We're creating a whole bunch of Grape 2s. We're going to distribute them across the United States. We have Kung over here. He's our new graduate student assigned to this project to, write the code, help Bill Engelke write the code to collect this and visualize this data. Rachel Bodeker from Case Western, she'll be the PhD student, or she is the PhD student working on this project. So she's kind of the new Christina Collins. And you can see where all the little black dots here where we're putting these grape stations, and the colored dots here are the midpoints. Those are our sampling points. So one last experiment I want to talk to you about. This is the time difference of arrival experiment. This also comes from Steve Serwin. So Steve Serwin, he spent a career as a research scientist and engineer over at Swiri. And he continues to consult, and he likes just making these measurements for fun, and he does just an amazing job. So what he wants to do is he's found that using a chirp waveform, it's possible to get the relative path length measurements even without a GPS disciplined oscillator. And so in this Eclipse TDOA experiment, we're asking pairs of stations to team up in small groups to systematically transmit and receive these customized chirp waveforms to make these measurements. And this is going to be a way that people who have regular, who actually want to transmit and not just receive, like with the grape, and want to do so in a systematic way on the amateur bands using regular amateur equipment that's not necessarily GPS disciplined, they can participate in this. So here are the science questions. What is the observed change in the effective F2 ionization layer height caused by a momentary blockage of solar radiation? Is the symmetry observed in layer height changes when comparing before and after eclipse layer heights? So the way you do this is, for this to work, you have to have multipath for this to work. So the multipath we're assuming is 1 hop and 2 hop off of a particular layer, so off of the F layer. So here you can see here's 1 hop off the F layer, there's 2 hops off the F layer. The 2 hops, of course, is going to take longer to get to the same place as a 1 hop, and the receiver here is going to hear the 2 signals added together. Down here, I know this is an eye chart, but what this eye chart is showing you is that if you are in the E region, you can't really measure the time difference between the 2 different hops. Really is not easily measurable. It's rather small. But when you get into the F region, you start getting long enough delays that you can actually measure this. And if you were to use a chirp waveform, so up here is an audio chirp waveform at 100 hertz per millisecond on top, and then on the bottom is the same waveform, 3 dB down, delayed by 1 millisecond. And so with that 1 millisecond delay, if you add those 2 up, the receiver would see a pattern like this, and you're going to get a beat frequency of 10 milliseconds. You can take that beat frequency and the sweep rate and other information, and you can calculate the time difference of arrival for the multipath. And then you can use that to then go and calculate these, relative heights of these and how they change with time. So it's really, really neat stuff. Here's an example where he did this calculation, not just doing the relative multipath, but again looking at WWV. Steve calculated the heights for the E region of 1 hop F and 2 hop F. You can see here's the trace it came from. There you can see the E region trace. There's the E region height. There's a 1 hop F. There's a 1 hop F, and there's a 2 hop F, 2 hop F. And it's really neat. If you do it at 3 frequencies simultaneously, you get very different results. You do want to do this at the lower frequencies, so this type of multi-mode splitting most reliably occurs below 10 megahertz, so that's where you get the best chance for this multipath. If you go higher than that, maybe you'll get one of the modes, but the other one will escape off into space. So the TDOA experiment is going to be concentrated on 4D, 75, and 160 meters. And so if you want to participate in this, you register at the HAMSI website. You go to hamsi.org/eclipse, and you can look for TDOA, and it'll get you here. Once you register, you'll eventually be paired or assigned to small groups that you're going to work with, that you're going to transmit your signal to and receive. You'll want to generate your own custom chirp waveform using our online Jupyter notebook. Stations will take turns sending and receiving these custom chirp waveforms, and then you're going to return your recordings to the AMSAT website for further analysis. And we are also looking for people to help with the analysis too. So after the eclipse, you can help us see what was going on there.
You should be a graduate mathematician.
Yeah, but we have a lot of it is things you can do. So here's to generate your custom waveform. You go to the website. You can be taken to this binder website, which will run the Jupyter notebook for you. You put your call sign and your grid square in there. It'll generate a waveform that has CWID for your call sign and grid square already built into it that you can then send to your radio through a sound card interface. Or if you have a flex radio, you can actually send the waveform directly without going through the audio chain. And so then that has certain advantages. And this notebook was put together by Christina Collins, KD-OXT, and Aidan Monteiro, KB3UMD. You don't really want to hear that, do you? Well, we'll skip that. so you can join us in a dry run approximately a month before the actual eclipse, and this will give everyone a chance to check out their hardware and software, make adjustments and updates well in advance. And so they're proposing, this particular group's proposing a test run September 16th, 2023 at midnight UTC. But details have not been finalized. If you register, you'll get notified when the groups. You'll have chances to talk about this. So, let's say you want to get involved with all of this. Of course, you can just participate in our experiments as we just talked about. You can also join our HamSci Google group. We now have over 800 members. You just go to hamsci.org, you press the big blue button, and then you can join the Google group. The other very popular way to participate is by joining in our weekly telecons. We have the Tangerine SDR telecon every Monday evening, 9 p.m. Eastern, which is currently 100 UTC on Tuesdays. But we always stick with the Eastern time, and then if it's daylight or standard time, we just stay 9 p.m. Eastern. So the Grape telecons are Thursdays at 10 a.m. Eastern, and the solar eclipse QSO parties are Thursdays at 4 p.m. Eastern. It's really great for you to be for people to come on and be involved because, we're looking for people to help out. Like we are looking for people who are, say, for the Tangerine project, we might be looking for people who have FPGA expertise. Verilog expertise.
In specific.
Yeah, we need Verilog expertise with people who are very good at FPGA timing. So if you are a person who identifies with that statement, I'm good at Verilog and FPGA timing, please come talk to me after the
We have a very interesting job for you.
Yes, we do have a very interesting job for you. So we have that, and then we also have, but other things like the SEQP scoring committee. I think last SEQP, I wrote all of the Python code to do the scoring for the SEQP, and it's kind of complicated when when some of the bonus points actually depend on you being spotted by these other networks, and so you have to go pull in all the data from the spotting networks and then compare it with the submitted logs. And we have Jay right here, who has been very kind and offered to write, requirements document. But then Jay's going to need someone to actually implement that requirements document.
Yeah, the goal will be, this is what you have to do,
Right.
not how you're going to do it.
A true requirement stack.
Yes. Yeah.
The requirement specification, and then of course, in accordance with the software V model, you're going to have a test plan to show that, yes, you really did meet the requirement.
So if you like writing software and you like contests and scoring, we have a job for you. So all sorts of ways to volunteer. And if you like data analysis, if you have your own thing that you're like, I think this is going to be a good way to study, this scientifically, like Jonathan has his VLF, that's great too. So finally, come visit us at Hamvention. We're at booth 5008, and we are with TAPR. We're right next door. We also have booth talks. The booth talks are actually held at the Youth on the Air booth in 4303. So there's alternating between, HamSci topics. I know there's ARIS topics and It's going throughout the day tomorrow. We have the Hamsat Forum tomorrow at 2:50 p.m. in room 4, forum room 4. And also, tomorrow morning, 9:30 a.m. at the Hamsat booth, we're going to do a group photo. So if you want to be in the Hamsat group photo so that you show up in my talk next year, like this.
The ladder is ready.
The ladder is ready.
Yep.
So, you can come join us. So finally, I'd like to thank all of our sponsors and supporters, the National Science Foundation, NASA, ARDC, all very generous. And most importantly, the members of the amateur radio community who've contributed to all of these projects. We cannot do Hamsat without you. So, thank you.
John Ackerman has had to flee the scene. There we go. And so we'd like to thank Nathaniel for another wonderful talk. We learn more and more every time.
Thank you.
And it's always wonderful having you here. Is there anyone from AMSAT leadership who would like to step up for some closing remarks?